workshop on open source space mission design tools this evening in beautiful Izmir, Turkey. Our next speaker will be Dr. Shyam Bhaskaran, and I would like to read your biography, Shyam, to introduce you to our participants. Dr. Shyam Bhaskaran is the supervisor of the Outer Planet Navigation Group at the Jet Propulsion Laboratory, leading a group of engineers responsible for the navigation of spacecraft that explore the outer solar system. His professional career began at the Jet Propulsion Laboratory in January of 1992 as an orbit determination specialist on the Galileo mission. Since then, he has been a member of and led the navigation team for several missions, including Stardust and Deep Impact. Dr. Bhaskaran has also been involved in formulating proposals for new mission concepts and developing innovative new technologies, serving as a principal investigator or co-investigator on a range of technology development efforts, such as high-speed kinetic asteroid impactors, terrain relative navigation, and precision autonomous navigation. Dr. Bhaskaran received his bachelor's and master's degrees from the University of Texas at Austin and his Ph.D. in Aerospace Engineering from the University of Colorado at Boulder. And this takes me home, Shyam, because that was the group where I worked in the 20th century. So when Dr. Mark Raymond and I were there together, so we might have crossed paths. You know, I just don't know what happened there. It was a very intense moment, but very beautiful experience. So I am particularly touched that you join us, and I would like to explain to the audience, especially my students, that fundamentally you're going to be hard-pressed to find anyone better in the world for deep space navigation in the solar system. Shyam is a mind of unique capacity, and we are deeply privileged to have you here, sir. Thank you so much for making the time, and I look forward to your presentation with eager anticipation. Dr. Shyam Bhaskaran.
Thanks very much for the introduction, Fabrizio. Appreciate it, and that was very kind of you to say that. So yes, I'll be talking about deep space navigation, and let me try to share my screen now. Hopefully this will work well. Let's see. And let's see. Okay, I don't know how is that.
We got it. Except that you are not on the slide number 1.
Ah, I'm not. You're right.
Well, that's it. Yeah, we go.
There.
Yeah. All right. Perfect. And you are not in presentation mode.
Yes, I'm going to do that right now.
Yeah.
Written presentation mode. How's that?
Yeah, we go. Perfect.
All right. Thank you. Perfect. Okay, great. Thanks, everybody. This is, as I said, this is an overview of deep space navigation. So as you can probably imagine, deep space navigation is a rather complicated subject. And what I've tried to do is put this into a forum that I hope that, you know, at the senior level colleges, the seminar is really designed for senior level college engineers. But I hope that I can speak at a level that, you know, a various range of people that understand. And certainly, if you have any further questions about it, feel free to ask. So with that, I will start my presentation. So first, I'll give you a little background on deep space navigation. I'll talk a little bit about mission design. So I should point out that, you know, navigating in space, you know, is somewhat analogous in many ways to navigating on the Earth. If you want to plan a route from, say, Izmir to Istanbul, for example, nowadays you can probably take out your cell phone and, you know, put on Google Maps and it'll plan a route for you. And in space, we do that same thing. We also plan a route before we embark on the trip. Once we plan that route, we start on the trip. It's like, you know, driving now. Now you plan your route out on your Google Maps on your phone, and now you start on your trip, and therefore you can see on your phone where you are exactly along the way. And of course, in there, the navigation is being done for you because of GPS satellites that tell you where you are exactly on the Earth, and you put it on a map. For us, navigation, we don't have GPS satellites out in deep space beyond the Earth, so we have to use a little different method. But basically, it's the same process where, we figure out where we are, we have a route that we want to go on, and then we embark on that route. And as we go along the way, we make corrections along the way. And I'll explain this in a few minutes. And then I'll give you a couple of examples of some missions, that we've navigated, just to see, give you a flavor of what navigation is like. So let's go to the first part of this, which is planning the route. As I said, the first step is always to, actually, I should tell before I do that, take a step back. Why do I call this deep space navigation, not just general space navigation? And the reason I say deep space navigation is to distinguish this between navigation and Earth orbit. If you have a satellite in Earth orbit, with GPS satellites, just like you do on the Earth, you can put a GPS receiver on a satellite in Earth orbit, and it tells you exactly where you are to very high precision, to about the several meter level. This data is geometrically rich, which means you have data from different parts of the sky coming at you. The data is almost always visible. You always have GPS satellites available in view, so that at any given time in space in Earth orbit, you know exactly where you are. The GPS receiver provides real-time solutions at a very high frequency. And you can use this positioning to then, if you string a bunch of positions together, the GPS gives you the position, you can get the velocity of your spacecraft also. And so the GPS is great for coverage in global coverage in low Earth orbit, can be used all the way out to geosynchronous orbit and even beyond. And even people can think that perhaps you can even do GPS at the moon as well. But once you go beyond that, lunar distances and beyond, you don't have GPS anymore. So now we go to what I call deep space navigation, which is a very different process than using a GPS receiver on the Earth or Earth orbit. Primarily, we do navigation using radio signals that we get from antennas at for the US, for 3 different complexes, these giant antennas that are located in California, in Madrid, Spain, and in Canberra, Australia. In addition, we also have these giant dishes that other countries and space agencies operate. Japan, for example, has a station at Usuda. The European Space Agency has stations in Perth, Australia, and in Malargüe, Argentina, I believe. And so, those other space agencies also have these space antennas. So we typically, sometimes, get data from them also. As I said, we use this for missions to lunar distances and beyond in the solar system, and also including spacecraft that orbit other bodies in the solar system. Now, one of the things that makes this different than GPS navigation is that, unlike GPS data, which is pretty much always available, the data from the radiometric tracking data from these antennas are not always available because there's 3 stations located around the globe, and there are very few of those antennas available. So, and you have lots of spacecraft out there, so they don't always get the time they need. So we have to schedule these stations very carefully. And therefore, the data that comes in that tells us what the spacecraft are, or gives us the data that tells us what the spacecraft are, is not continuous. Sometimes, if we're out in deep space and we're nothing much is happening, we may not get data from them every more than once a week or once a month. If something critical is happening, something like an approach to Mars, for example, we might get data continuously. But the thing is, it's not constant, and it's also not geometrically rich. Unlike GPS satellites, there's 24 of them orbiting out there. You get data from all different sides. This is one station looking out to one spacecraft, and so all you get is one single dimensional piece of data there. And you have to infer from that a lot of different characteristics about the spacecraft orbit. So it's a much different problem than the GPS, and it makes the deep space navigation somewhat of a unique situation that we have to solve. So, as I said, starting off, that the first part of going out to deep space is planning the route. As I said, this is planning analogous to planning the route on a road map or charting across the ocean on a ship. But our map in this case is a mathematical model of a spacecraft trajectory in the solar system. And we do that taking into account all the forces which act in the spacecraft. So hopefully, if you're in high school or college physics, you know that there's various gravitational forces acting on a spacecraft in space. What we call the central body force is the central planet the central planet that you're orbiting around, if it's the Earth, for example, or Mars, or if you're out in deep space, is the gravity of the sun itself, is a primary gravitational attraction force, and that's the biggest force acting on the spacecraft. But in addition to that, even if you're in deep space or if you're orbit around the Earth or on the planet, all the other gravities of the planets also affect your spacecraft course. So with the mathematically modeled, not just the central body acceleration, but acceleration from all the different planets acting on the spacecraft. On top of that, the gravity field, as we call it, of a planet is not spherical. It's not like a single point mass concentrated in the surface. All bodies are, in a sense, kind of lumpy. And because of this lumpiness, they have different varying gravity, what we call the gravity field, which perturbs the spacecraft in slightly different ways. So we have to account for that as well. There are also some relativistic effects that happen on the spacecraft because we are out in deep space and we're traveling at high velocities. There's some Einsteinian relativistic effects we also take into account, although they're relatively small. On top of that, we also have what we call non-gravitational forces acting on the spacecraft. This includes thruster firings. So the spacecraft will periodically fire thrusters to change its course, and that, of course, affects the trajectory of the spacecraft. The spacecraft can also, in order to maintain its attitude, it has to rotate around, different directions to, point the solar panel to the sun or point an antenna at the Earth. And sometimes these are done using thrusters. So those thrusters, once again, acts as a force in the spacecraft. There could be gas leaks. There could be fuel leaks in the spacecraft that vent out, and that can cause a force in the spacecraft. There's solar radiation pressure. The sun's photons out there have momentum, actually, and the momentum actually pushes on the spacecraft. And I think the previous lecture you heard was from Bruce Betts on the solar sail. And that same force, they use that very nicely in solar sails to push the spacecraft. For us, it's actually a disturbance instead of something that we have to use. We have to take that into account. Now, we don't have the big solar sails that pushes that as much, but even in our small spacecraft, it still has some force, from the solar pressure, and we have to take that into account. And finally, if you're orbiting around a body like the Earth, for example, or Mars, each of these bodies has an atmosphere. So the atmospheric drag also affects the spacecraft and will pull on it and change its course. So all these forces we take into account, and then with all that, we then map a trajectory out that takes all these forces into account, and that's our planned route. So here's a simple example of a planned route to Mars. So I don't know if you can see my pointer or not, but hopefully you can. But if not, I'll try to point out here. So we
can see it. We can see it.
Okay, great, thank you. So here you are, Earth at launch, and you have Mars at launch. So now we plan our route out, and the point is we want to get to Mars. We want to launch from the Earth. It takes about 6 to 9 months to get to Mars. We plan the route such that as we launch from the Earth, it takes about 6 to 9 months to get to Mars, and we want to plan it such that Mars is there when you get that arrival. And then so this is a fairly simple trajectory planning route. From Earth to Mars is very simple. Almost like what we call the Hohmann transfer, 180-degree transfer round. And it's all important. It's all in the timing. You launch exactly when that Mars is going to be there when you get to that point. And this kind of a mission has different mission phases. There's a launch phase, there's a long cruise phase, and there's an approach phase that gets to Mars at arrival. So this is a pretty simple trajectory, very easy to see. Here's a little more complicated trajectory. This is actually a mission called Europa Clipper, which is going to launch in 2024. And this is going to launch from the Earth, go to Jupiter. So we have to, this is about what I believe a 6-year trajectory. So we launch in 2024 and get to Jupiter in 2030. But it's not just getting to Jupiter. So we also do a flyby of Mars to give us a gravity assist boost, to give us a little more acceleration to get to Jupiter. Then once we get to Jupiter, on the right-hand side here, what you see is what's called a tour of Jupiter, where we fly by all, many of the Jovian satellites. And the goal is to fly by Europa many, many times. So there's actually 51 flybys of Europa in there. And as you can see here, this is a very, very complicated trajectory involving many flybys of all the Jupiter moons, and eventually flying by Europa 51 times to do science at Europa. The lowest altitude flybys is a mere 25-kilometer altitude above Europa, with a ground speed of about 4.4 kilometers per second. So you can see here, this is a very, very complicated map that we're drawing here to do a tour of Jupiter. And this takes quite a bit of time and effort, obviously, to generate this kind of map. Here's another example. This is something called a low thrust mission. This is for the upcoming Psyche mission. Now, unlike most missions, which you launch from the Earth and you wait a long time before you do any kind of trajectory correction maneuver, low thrust uses something called ion propulsion system, which hopefully you all have heard about, which applies a small amount of thrust, but it happens over very, very long periods of time. And so it's almost like a solar sail in a way, in that the thrusting is happening constantly throughout the entire mission. And this makes for also somewhat of a more complicated trajectory. But here's an example here where we launched from the Earth in 2022 in August coming up. The launch is actually coming up. We spend a long time, doing a few months doing a quick check out of the ion propulsion thrust system. Then we thrust for many, many months. We do a flyby of Mars in May 2023 at 500 kilometers altitude. Then we thrust again for long periods of time. And we finally approach the asteroid Psyche. And then we capture into the asteroid Psyche, and then all this whole time we're doing orbital operations around the asteroid Psyche, and we'll change the orbits. I think there's 4 different orbits in there. They go from a fairly high orbit to a somewhat low orbit, and all the orbit transfers are done using low thrust. And this is an example, a different kind of a trajectory that we fly. So these are all the kinds of examples of the kinds of missions that that we call the reference trajectory. This is what we want to do. And that's the first thing we always do in any mission, is to decide these reference trajectories to tell us, okay, here's ideally what we'd like to do. And the next part is the navigation part is, so once we actually launch this trajectory, now we have to fly it. We have to go back and make sure we achieve this reference trajectory. And that's what we call the navigation. So flying the spacecraft from launch to end of mission, which includes reconstructing the position and velocity of the spacecraft up to the current time, which is what we call orbit termination, or determine the orbit of the spacecraft. Using that determined orbit, now we have to predict the future path of the spacecraft, saying where's it going to go over the next few days, next few months, next few years. We have to predict that future path. We compare where it's actually going to where we wanted to be from that mission design that I told you earlier. And we can, and the orbit determination tells us we're not going to be exactly where we wanted to be, and we're not going to go exactly where we want to go. We have to make course adjustments along the way. And this is what we call the flight path control. So the 2 steps in the orbit determination process are determining where we are and where we're going, comparing it to where we wanted to be, and making corrections to that. So for the orbit determination part, we use the tracking data to compute spacecraft's current trajectory. As I said before, we use antennas, the 3 antennas, the DSN antennas we call, and other agency antennas, to get tracking data. And the different types of tracking data we get are what's called Doppler. The Doppler effect, I hope you're all familiar with that, is that effect as the frequency of a signal as it's coming towards you is higher, and as it goes away from you, it's lower. And you've all heard that effect as you're watching a car coming in or a train coming towards you and away from you. That the pitch of the sound changes because of that of the Doppler effect, and we can precisely measure that Doppler effect on radio signals. And that the measurement of that Doppler effect tells us what the velocity of that spacecraft in the line along the line of sight to that spacecraft. The other radiometric data type we have is called range. The range measures the line of sight distance of the spacecraft. So basically, we send a signal out with a certain pattern. We send it to the spacecraft. The spacecraft takes that and turns it back around, sends it back down to us. And when we see that pattern coming back, we correlate when the time it took for the signal to go up the spacecraft and down, and we know the speed of light. So that tells us the distance of the spacecraft, the range of the spacecraft. Those are the 2 main data types we use to help determine the spacecraft's orbit, the Doppler and the range. We also use a couple of different things that also help us refine that orbit. One is called delta differential one-way range, or called delta DOR. And what the delta DOR does is an interferometric data type. So what happens is the spacecraft sends a signal down from the spacecraft down to the Earth, and we have 2 tracking stations on either side of the Earth. And And one tracking station will receive that signal just a little bit before the other tracking station. And if you do the math, look at the geometry, what that does is eventually tell you that it tells you the angle in the sky where the spacecraft is at. And finally, the other final data type we use is something called optical data. And here, the spacecraft has a camera that it carries on board with it. It takes a picture of the target body against a star background, and that picture tells us where the spacecraft is relative to that target body in an angular sense. So all these data types, each gives you a single piece of information that eventually we use to reconstruct the entire orbit of the spacecraft. And then, as I said, there's flight path control. So at predetermined times in the mission, we compare the predicted course with the actual course. And if it's outside of some tolerance that we want to, we're not quite where we wanted to be, we compute a maneuver to retarget to where we want to be. And we can use various techniques to optimize this trajectory so that we minimize the fuel usage. And we obviously keep track of the fuel usage as we go on the trajectory, so we don't want to run out of gas along the way. So as I said, the navigation data are called scalar variables. In other words, they give you a single piece of information, either the range of the spacecraft or the velocity of the spacecraft or an angular measurement there. But we're trying to get the state of the entire spacecraft, which is a vector. In Cartesian coordinates, there's 3 Cartesian coordinates of position and 3 Cartesian coordinates of velocity, so a total of 6. So there's 6 states we have to estimate the spacecraft using data the single scalar variables. And in addition to that, we also need to estimate, as part of this whole process, additional parameters that tell us where the spacecraft is going. Examples are, if we fired a thruster, how much thrust did we fire? There's solar radiation pressure. How much acceleration is that giving us on the spacecraft? If we're on a different planet, for example, it's a gravity field. We don't know it exactly, so we have to estimate the gravity field also. So we have to estimate all these parameters along the spacecraft trajectory. And we have to do that using these scalar variables. As I already said, Doppler range of the primary data types, augmented with delta Dora and optical data types. The amount of tracking data we get depends, greatly depending on the mission phases and requirements. As I said, critical times, launch or approach or flyby, we require nearly continuous levels of tracking. In quiet cruise, we may use as little as one tracking pass, every few weeks. So, here's a little more detail about a Doppler measurement. The Doppler measurements are made when a single tracking station sends a signal out to the spacecraft. The signal is got by the spacecraft, and then it turns around, sends it back down. And because of the velocity of the spacecraft, that signal is frequency shifted, and we can measure that frequency shift, and that tells us the velocity. As I already explained, also the range measurement, it just measures the round trip light time for a signal to get to the spacecraft and back down to the Earth. And this kind of tells you, this kind of geometry, the typical geometry, what it looks like. Spacecraft is out there. Here's a DSN tracking station on the Earth, rotating around with the Earth. And what you'll see here is that if you plotted this, what you'll see is this kind of, this sinusoidal signature of the velocity, and that's because the Earth is rotating. So, in addition to the spacecraft's velocity, the Earth is also rotating under it. So it's got, a diurnal signature on that velocity. But if once again, if you work through the math, the amplitude of that signal and the phase of that signal tells you information about where the spacecraft is in the sky. This is an example of VLBI. It's a little more complicated. I think I'll skip this plot for right now. But basically, I explained to you earlier, you get a spacecraft sending a signal down, and it received the 2 tracking stations of the Earth receive the signal at 2 different times, and that tells you the angle of that spacecraft, in the sky.
Oh, you can talk about this. They can take it. We got physicists also in the group, so that I would love for them to hear this if you can.
Oh, actually, yeah, I would talk more about it. Maybe I'll have questions, but I want to get through my presentation also. So
of course,
skip the details of this and surely feel free to ask any questions.
Of course.
So one thing important about this is time. So, keep in mind, we're measuring the time, for example, for range, and measuring the time it takes for a signal to go up to the spacecraft and back down. And it's very important that we keep very accurate time, because any error in the time tag, if there's, will basically translate to an error in the range. So we have very precise measurements. So that we have to have very, very accurate clocks. So the tracking stations at the deep space complexes are equipped with extraordinarily stable clocks. They have 4 atomic frequency standard clocks in each of the stations. There's a hydrogen maser that serves the source for all the timing for getting the precision frequencies and provides the frequency reference for the station. And each site synchronizes the clock with UTC, which is the common measure of time via GPS signals. But the typical accuracy of the clocks of the DSN stations are about 10 to the minus 14th, which is extraordinarily accurate. The clocks on spacecraft are not as accurate. And so that's why we have what's called two-way communications. The DSN signal to the spacecraft, the spacecraft sends the signals back down. And because all the time tags are happening at the station itself, we have very accurate clocks. There are new technologies, something called the DSAC, the Deep Space Atomic Clock, which has been tested in space right now, which will not approach the same accuracy as the clocks of the DSN, but will approach accuracies that are almost good enough for us to do what's called one-way tracking, where instead of the spacecraft signal from the DSN signal sending the signal from the ground to the spacecraft and back down, the spacecraft sends the signal by itself to the ground. It's one way. And the advantage of that is that, it takes less time. You need less tracking time to have the spacecraft send the signal by itself as opposed to the DSN signal. So, but this requires accurate clocks. We're getting to the point now where the DSAC, for example, might be useful in future missions, that we can use this more often with this accurate clock. Finally, as I mentioned, there's what's called the optical navigation, which uses cameras to take images of natural bodies against the solar system background. And as I said, this provides a measurement of the angle between the spacecraft and the target body in an inertial reference frame. We have stars in the background, and some people always ask me, can't you use stars for navigation in space? And the answer is no, mainly because the stars are so far away that the parallax, so that the angle, if you're looking for an angular measurement, if you're on one side of the solar system or on the other side of the solar system, the stars are so far away, you get no difference in the angle for all practical purposes. So they give you no information about translational motion in the solar system. However, they do make a good reference to give you the inertial pointing direction of where your spacecraft was pointed. Because as you can probably imagine, if you want to measure the angle between you and a target body, if the pointing that if your camera pointing is not what you thought it was, that'll cause an error in that measurement. And so therefore, the stars provide an inertial reference frame that you want to make your measurements on, and the target body provides the angular parallax measurement. The accuracy of that data type depends on the ability to locate the center figure of the target body. And I think I'll show a picture of this in a second to explain that in more detail. The optical navigation is primarily used on approach to target bodies. And it's really important because, for missions to Mars, we know where Mars is to very high accuracy. But if you go out to the farther parts of the solar system, say to Uranus, Neptune, we don't know where the planets are at high accuracy. So say you want to make a flyby of 1,000-kilometer altitude of say a satellite of one of the moons, for example, which we don't know where it is. If you don't know where that is to 1,000 kilometers, you're not going to be able to fly by very accurately. So we have to, in those cases, have optical data, because the optical data tells us where the spacecraft is relative to that target body. So even though you don't know where the target body is in inertial space, you know where the spacecraft is relative to that target body using the optical navigation. So the OpNav is very, very useful for missions that go to bodies which we don't know the orbit of. And these include the outer planets, satellites of all the outer planets, and especially asteroids and comets. And also, if you're orbiting a small body, for example, an asteroid mission, like recently the Hayabusa mission went to an asteroid called Ryugu, the OSIRIS-REx mission went to an asteroid called Bennu. And if you're orbiting these very small bodies, all the landmarks in those bodies provide a very good navigation data type. And so we use optical navigation extensively for small body missions as well. So as I said before, and this is an example of an optical data type. You take a picture of a star, of the stars and the target body. And here, the target is actually a little spot over here. It looks exactly like a star. This is what's called an unresolved body, because it's so far it's like a point source. And here are all the predicted locations of all the stars. Now, because the spacecraft attitude is not exactly where we thought we were, where we thought we were taking the picture is not quite where the picture was actually taken. So if you look at the right-hand side, and this is what we do on the ground, we then align all these patterns here. If you look very carefully, you can see this pattern is actually there. And if you shift everything up to the upper left slightly, that direction, now you can see all the where we thought the stars were as where the stars really are. And that now gives us the inertial direction of where the camera's pointed. But the target body, here's where we thought the target body was going to be, but actually it shows up over here. This is the parallax. This tells us that the spacecraft is not where we were relative to where the target body was. And this is why we have to adjust the spacecraft trajectory in the orbit termination process to now correct that and make this alignment right. Okay, so that described kind of the data types we use. This kind of is an overview of what the whole process of orbit termination is. So here out in the real world, we have a spacecraft, flying out in space somewhere, and then we have the DSN and transmitting signals back and forth to the spacecraft. And here in our orbit termination process, we have our model world. We have our dynamic models, our observation models, and we take our given our models, we try to predict what our data is going to tell us. That's our predicted observations. We get the tracking data, that's our observations, and we compare the two. So if our spacecraft's exactly where we thought it was, then with our data our predicted data and our actual data we got should match each other to some level with just some random noise around it. When it doesn't do that, that means that if they don't match, we then correct our models. We correct the trajectory, we correct the forces that act on it, and we redo that. We refly the spacecraft trajectory and we compare it again, and do the same process over and over again until we match. Then our residuals, meaning the difference between where we thought we were and where we are, match up exactly. That means our data type is matching our data, our observation data matches where we really are. Now we know where we are. That's the orbit termination process. Then we can go to the flight path optimization that tells us, okay, we are now we know where we are. We aren't where we wanted to be. Now we correct the trajectory. And so this is the whole process of orbit termination. It's an iterative process. We continually do this where we compare the observations against the reality and then correct our models using the least squares process. And that least squares process gives us the spacecraft trajectory and gives us an uncertainty estimate on top of that. So, the process that all our navigators use, we look at the residuals of the tracking data and the solution, and it's just, it should display no signatures or trends. The data should look, should have a scatter around the zero mean. Any outliers must be removed. The data weighting we use in the least squares process, must match the scatter. Are the estimated parameters sufficient set to accurately model the trajectory? Now the data solution sensitive to dynamic and media errors. So basically we go through this process of steps to determine whether our solution is correct or not. As I said, it's a least squares process. The least squares process does not have to be accurate. It can just fit the data. That doesn't mean that your orbit is correct. So we have to go through all this very detailed process of checking all these things to make sure that we actually got the right solutions. So the correction of the estimated parameters make physical sense. For example, we shouldn't solve out to a negative solar pressure. The uncertainties we put in the least squares process should be of appropriate magnitude. And so this is all the kind of least squares process we go through for the navigators to check to see whether the estimate is correct or not. Here's an example of what we do. So this is exactly what we see. This is Doppler tracking data. So in our first process, what we've done is we have a trajectory that we think we're on. We get the tracking data from the DSN and we plot it up and say, what does it look like? The residual of where we thought the tracking data is telling us to where it shows us, and it looks like this. So you can clearly see from here, this is not random noise. You can see various signatures in here, various odd things going on here. So now we know that we have to do a correction to our models. So we go through this iterative least squares process and we iterate and iterate until we get to the point where it looks something like this. This now tells us that our tracking data, we fit the model perfectly. It's flat across the entire time span. what you see here is mostly random noise. If you zoom in on any one of these tracking paths, you'll just see a scatter of points there that look more or less like random noise. And this tells us that our fit is now good, and we now know where the spacecraft is. So once we get that, we estimate a spacecraft, which typically we estimate in Cartesian coordinates, x, y, z, x dot, y dot, z dot, centered centered in our primary gravitationally attracting body. But in order to help us figure out where we are going, we always take that solution and map it forward to somewhere in some coordinate frame of interest. For interplanetary trajectories, which go to a planet, something we typically use, and you'll see commonly if you ever talk with navigators, is something called the B-plane. And so the B-plane is very simple to understand. It's like a target plane, like a bullseye basically. And we want to fly by in a particular point on that bullseye by a planet, or do an orbit insertion in that particular point on a planet. And this is called the B-plane. And so we take our Cartesian position and velocity and map it forward to the B-plane to tell us if our trajectory is on the right path, a path or not. That's just one example of a mapping. The other mapping could be equator longitude crossings if you're an orbiter around a planet, for example, or an orbital period. You want to maintain an orbital period of X number of days or hours or whatever it is around the planet, and we can take that Cartesian state and rotate it into orbital elements. It gives us the orbital period. Various things we can map the solution into. And here's another example of the maneuver design or trajectory correction process. So we launch the spacecraft from the Earth. We have our planned path over here, and somewhere over here, during this time we're doing orbit determination. Here we telling us where the spacecraft is. We map it forward to the target planet of question, to the B-plane, for example, and then we know we're not exactly on the right path. We design TCMs along the way to target us back. For something like a Mars trajectory, we typically have anywhere from 4 to 6 trajectory correction maneuvers, or it's called TCMs, through the approach phase. As we get closer and closer to the planet, we know better and better where we are, as we're approaching the planet, and therefore we make fine-tuned corrections that get us to where we want to be. And I'll show you an example of that in a few minutes here. Here's an example of a Mars B-plane, for example. So we've done an orbit determination. We're mapping it forward in time to where it's going to be, at the Mars B-plane, and we figure out are we in the right spot or not. So, as an example, for Mars entry, we have a target aim point, which is somewhere here between like an inner skip out zone and an outer skip out zone. So, if you're inside this spot here, you're going to burn up in the Mars atmosphere. If you're outside the spot over here, you're going to skip out and go somewhere else. So we map our trajectory forward into the B-plane and say, where are we? So let's say we're over here. We are outside where we wanted to be. So then we would do a maneuver to target us back to where we want to be. But let's say that we mapped ourselves and we're over here. Here, and these ellipses are uncertainty ellipses that tell us, this, for example, it could be a 1 sigma uncertainty ellipse. And that tells us that we're here, but our uncertainty is like this. Well, we're pretty high, pretty confident that we're going to be inside, our target zones. We probably would not do maneuver in this case. Here's a more confusing case. Our target point, where we're going to predicted is here, but our uncertainty ellipse is here. Now, do you do maneuver or not? Because what if you're over here, you won't want to do maneuver, but if you're over here, we wouldn't want to do maneuver. And this is one of those things that is a very difficult thing to assess, and this typically takes meetings and lots of conferences to figure out, should we do a maneuver or should we not do a maneuver? And there's no simple answer to that question here, but this kind of gives you an idea of the process we do to figure out where we're going and how we want to get to where we want to go. I want to take a little bit of diversion to talk about solar system bodies. As I mentioned before, if you want to get to any planet or body in the outer solar system, you have to know where the body is. It's not just good enough to know where the spacecraft is. So there's a whole large effort, and we have a section we have a group in our section that is their entire time is spent figuring out where the orbits are of the natural bodies. So we have a service, the ephemerity service, the JPL. It's a worldwide service. It's continual long-term activity. They take measurements from all around the world, including astrometric images from observatories, radar measurements that bounce radar signals off bodies, signals from spacecraft or near a planet or body. and they will basically estimate the ephemerides of all the planets and all the natural bodies in the solar system. They'll provide to the navigation teams with some level of uncertainty on it. So this is an important part of the navigation process, which maybe most people aren't aware of. The other part is gravity models. So as I said before, planets have very lumpy gravity fields. So using tracking data from spacecraft, the SSD group will refine gravity models, because this helps us plan trajectories around planets, for example, to have more accurate gravity models. This is a kind of an eye chart, but it tells you how complicated the whole orbit determination process is. We have inputs from all different sources, from the DSN. We have media calibration data. We have the natural body ephemerides. We have information from the spacecraft. So what it kind of shows you is that the whole process is very, very, very complicated. This is why it takes teams of navigators on any mission to do this whole process. And we have our main software, our orbit determination software is called Monty, that does all the orbit determination, that takes all these inputs in and computes those orbits. We have optimization codes called CADO and that optimize trajectories. We do maneuver design in Monty. And so we interact with a lot of different teams and a lot of different organizations to try to get the navigation solution done. Now I want to go into, I have a few minutes for some quick examples here. So hopefully all of you remember, if you're a space enthusiast, you remember the Mars missions M2020, which landed at Mars about a year ago. These are actual data from that Mars mission that show kind of what happened. So here's a picture of the Mars B-plane, and there's Mars equator. So the idea was the spacecraft had to hit a target point in order to get the right entry conditions for Mars. It had to hit a very, very narrow target point just outside of the Mars atmosphere. And here you can see the blow up of the, over here. Now you zoom on this one little area over here, and here's the blow up there. And there's this little sliver of area we had to hit. Now here's a blow up of that, and you can see here, this is a very kind of a complicated chart, but it tells you the kind of box that the Mars navigation team was aiming for. So EFPA is entry flight path angle. They had to target an entry flight path angle of negative 15.5 degrees. And the margin on that was, I believe, about 0.05 or something degrees. I can't remember the exact number, but it's a very, very narrow corridor that the navigation team had to hit in order to get the right entry conditions at Mars. You can imagine here that this is it's a very, very precise entry. And so the corridor they had to hit there. So as they were approaching Mars, this is what it looked like 10 days out. So here's all the, they did various solutions where they, tried various different, data types and data weights, and they do a lot of mixing and matching of data, because you want to make sure that, no single data type is causing problems. So they do all sorts of multiple solutions, and they plot them up. And this is, I believe, like I said, at 10 days out. Here's that corridor they're trying to hit, and here's like all the different solutions. You can see they're big ellipses. Now, at 10 days out, they didn't have the accuracy to get the exact flyby, exact entry conditions, but that's okay. They expected that. So, what they're basically doing is making sure that they're still, going in the center of this corridor. Now, here's the situation a few hours out. Now, you can see the solutions here are inside this corridor here, and all the solutions are falling inside the corridor. Here are the different solutions here. Here are the different error ellipses. And what you can see here is that at I think this is what, a few days out or a couple of days out, that they have now hit their entry condition. They can know now that they are doing okay. And they did not do a final TCM, for example, to recorrect this trajectory, because they were close enough to their flyby to their entry condition. But you can go back and see how you go from that to that. As you get closer and closer to the planet, your data gets more and more accurate, and in the end, it was successful. And I will touch now briefly on something called autonomous navigation. So all the things I've talked to you about right now are navigation done on the ground in the loop navigation. We have teams of navigators on the ground that take the tracking data. They do the orbit determination solutions. They perform maneuvers. In some situations, that ground and loop navigation may not be capable of achieving mission objectives. It can be due to several things. One of the biggest is the round trip light time. it takes, as you all know, light travels at a finite speed. And so if you're out on the solar system somewhere, it takes several minutes or hours for a signal to go from the Earth to the spacecraft and back. And in some situations, that delay because of that means that your navigation accuracy is not good enough to achieve mission what you want to achieve in the mission. And I'll show you an example with deep impact in a minute here. So in order to fix that, you then put the navigation on the spacecraft itself, so it computes its own orbit and its own maneuvers to achieve the desired target. This system, we have built a system at JPL that do onboard autonomous navigation, which we call AutoNav. Right now, AutoNav is based purely on optical data, because the optical data does not require a link to the Earth. You can put the entire navigation process on the spacecraft using a camera, onboard camera. So it does not require the use of a DSN antennas. It does not depend on Earth-based parameters. It's all entirely self-contained in the spacecraft. And we developed the system back in the mid 90s on a mission called Deep Space One. We first demonstrated the use of onboard AutoNav, and we use it for a certain portion of the cruise of that mission and the flyby of Comet Borrelly. Then we also use it subsequently on several missions. Stardust, we used to track the comet, track the nucleus of Comet Vil2 during the flyby, and this had to be done on board because we're doing this very fast flyby, and you cannot, the ground-based navigation is not good enough to know where you are, to keep the object's image in the camera field of view as you fly by it. The most difficult use is something called Deep Impact, a mission called Deep Impact, where we basically had to hit the nucleus of a comet at a speed of 10 kilometers per second. They're about, I think, 36,000 kilometers per hour, and it hit a 7-kilometer target at that speed. And with that kind of requirement to hit that target at that speed, we could not possibly have done it on the ground. So AutoNav was used for that. A mission called OSIRIS-REx, which went into orbit around asteroid Bennu. They had a Lockheed Martin, the company Lockheed Martin built a version of their onboard navigation system in order to achieve landing on the comet, landing on the asteroid to a precision of 1 meter or so. And a mission called DART, which is in flight right now, is a planetary defense demo, and it is going to demonstrate kinetic impactor technique to basically hit an asteroid. And DART is going to hit the secondary of a binary asteroid system called Didymos, which is, I think, about 80 to 160 meters across, a very small target at a speed of 6.1 kilometers per second. And they have to have their, the applied physics labs building that spacecraft, and they have their own AutoNav system called SmartNav, which is going to be used to basically guide the spacecraft onto an impact on the secondary. So these are all examples of what onboard autonomous navigation does. I'm going to go back to the Deep Impact example. So the Deep Impact spacecraft were 2 spacecraft. There's a mothership and an impactor. At a day out prior to the impact of Comet Tempel 1, the mothership released the impactor and diverted itself to do a flyby so we could actually watch the impact. So the spacecraft, the impactor released, and then a day out, at about 2 hours out, the autonomous onboard AutoNav system was turned on. It used optical data to track the nucleus of Comet Tempel 1. It performed 3 trajectory correction maneuvers at 90 minutes out, 35 minutes out, and 12.5 minutes out to impact the comet. Meanwhile, the flyby spacecraft used onboard AutoNav to track the nucleus in the flyby to watch the impact as it happened. And it was also, quite successful. And this was a mission flown in 2005. And if this works, I'm going to try to show a video. This is what the impactor on Deep Impact saw as it came in. Tell me if this. So you can see here, as the spacecraft is coming in, it's tracking the comet nucleus, and it's going to do maneuvers here to now target at the nucleus. And you can see here that it's going towards a spot right up over here, and the final maneuver is done, and it came in, and these images were streamed to the Earth through the flyby spacecraft. This is the last image that the impactor saw before it hit and caused a big flash on the flyby. So I'm just about running out of time, and I'm just about finished here. So deep space nav techniques, they've been used for up to 60 years. We use these techniques to navigate missions to pretty much every planet in the solar system, plus asteroids and comets and Kuiper Belt objects. The techniques were largely pioneered at JPL, and really the techniques I'm talking about here are used by pretty much every space agency that flies missions around to the solar system. Any future changes, changes to our navigation system is likely to be evolutionary rather than revolutionary. I think there'll be more use of autonomy, the one-way radiometric using DSAC. And there's some interesting techniques that are out there that are theoretically possible, called pulsar-based navigation, stellar navigation. And these are good things in the future, but they probably won't be used for another decade or so at least till they're really available. And even then, we'll be using our ground techniques for quite a number of years in the future. So with that, I am now completed, 5 minutes to spare. So thank you. And I guess there's time for questions. I'd be happy to answer any questions.
Well, thank you. It was a fantastic ride. I appreciate the information that is the best that one could possibly obtain on the subject. I really appreciate it. Just a couple of questions.
Sure.
One of them is, I think that I have a student who had a question about the Jupiter environment. So maybe we need to have probably the student to speak needs to be made. I don't know. Can you go ahead and ask the question?
Yeah, I may ask.
Okay, go ahead.
Thank you for your presentation. First of all, I was investigating the Europa Clipper mission a lot because of my interest in Europa. Could you briefly explain how could be the navigation or communication data will be affected in the harsh environment of Jupiter? Because there is not only a gravitational field of Jupiter there, there are also Ganymede, Callisto, and Io, as you know.
Yes. So for Callisto and Io, what did you say about those?
Because they also have gravitational field affected on Europa Clipper, so it's a harsh environment, and how could it be survived?
Yes, so we do model the gravitational structure of not just Jupiter, but all the satellites as well. And in fact, we not only model the gravitational field of the satellites, the point mass, but we also model its gravity field in several cases. So we do take all that into account when we do the trajectory design for the Clipper mission. So it is complicated, but we've already been, we've flown through Jupiter already. The Juno mission is flying on there right now. The Galileo mission flew through the Jupiter system back in the late 90s. So we have information about that, from the gravity fields of all the satellites from those missions. And so we use that, to help us fly. I think the other thing you may be thinking about is the radiation environment of Jupiter. And this would be a problem if we're coming very close to Jupiter with the high radiation. But in the Clipper's case, it's staying fairly, decently far enough out that the effect on the tracking data from the radiation environment is not as much as it would be if it's going really close in, for example. So these are all things that we do model when we take into account when we fly through the Jovian system.
Thanks a lot.
And I have any other students? Okay, I just had one, Dr. Bhaskaran, concerning the relativistic corrections, because we have some students here who have taken special and general relativity from me. My question is, can these corrections be used to confirm the general relativity theory? Are they good enough?
Yeah, that's a good question. And I think people have tried to do that. And I don't know enough detail. You probably know more about it than I do. Perhaps when you worked at JPL, there were people I remember trying to do that. I can't give you much more detail about it because I honestly don't know. I only know that various people have used information from these spacecraft to try to confirm some of the parameters of the general relativity theory. But I think the data is not strong enough for the most part to do that, is my guess. But once again, I'm not an expert on it, so I couldn't tell you for sure.
Thank you so much. I appreciate it. So there is another possible frontier there,
yes.
Maybe.
Right.
All right. Well, thank you so much, sir. It was a wonderful presentation, and I would like to tell you that you are welcome to visit us, hopefully in Izmir.
I would love to visit at some point.
Turkey is a beautiful country, and you will be most welcome here. And we hope that you repeat an updated presentation in person in the future.
Okay, thank you very much.
Thank you so much again. I appreciate it. Thank you.
All right. Bye.
Thank you. Bye-bye. So we will stop this